For centuries, the compass has been our guide, a steadfast tool pointing towards the north. It has been an essential instrument for explorers, sailors, and adventurers, helping them navigate through uncharted territories and across vast oceans. But what if I told you that north isn't as constant as we think? The direction we rely on so heavily is actually more fluid and dynamic than it appears. The magnetic North Pole, the point to which compasses actually align, is not fixed. Unlike the geographic North Pole, which remains in a relatively stable position, the magnetic North Pole is constantly on the move. It's on the move, and it has been for as long as Earth has spun. This movement is driven by the complex and dynamic processes occurring deep within our planet. Think of it like this. Imagine trying to navigate with a compass that points to a target that's always shifting. Imagine a giant bar magnet inside our planet, slightly tilted off axis. This internal magnet is responsible for generating Earth's magnetic field. That's a simplified picture of Earth's magnetic field. The reality is far more complex, with swirling molten iron in the outer core creating a constantly changing magnetic landscape. The magnetic North Pole marks one end of this imaginary magnet. It's the point where the magnetic field lines converge and point vertically downwards. Now picture this internal magnet slowly shifting and wobbling over time. This movement is not random but follows a pattern influenced by the dynamics of Earth's core. That's the reality of our planet's magnetic field. It's a dynamic and ever-changing force that affects everything from navigation to animal migration. The magnetic North Pole's journey is a slow and meandering one, but it's a journey nonetheless. Over centuries, it has wandered across the Arctic, shifting its position gradually. For the longest time, it drifted at a leisurely pace, averaging about 9 miles per year. This slow movement allowed navigators to make minor adjustments without much hassle. This movement was slow enough that we barely noticed its effects in our daily lives. But then, something changed. In recent decades, the magnetic North Pole's movement has accelerated, causing scientists to take a closer look at this fascinating phenomenon. In the mid-1990s, the magnetic North Pole decided to shake things up. It went from a leisurely stroll to a brisk walk, picking up speed to an average of 34 miles per year. This geomagnetic jerk, as scientists call it, was unexpected and sparked a wave of curiosity. Why the sudden acceleration? Just as we were getting used to the idea of a speedier magnetic pole, it threw us another curveball. In recent years, the pole's movement has slowed down considerably. This deceleration has puzzled scientists, adding another layer of complexity to the already intricate dance of Earth's magnetic field. This back and forth of acceleration and deceleration is a reminder that our planet is a dynamic system, constantly evolving and changing. It's also a testament to the power of the forces at play deep within Earth's core, forces that drive the magnetic field and influence its every move. To understand the magnetic North Pole's wanderlust, we need to journey to the heart of our planet. This journey takes us deep beneath the surface, where the true dynamo of our world lies. Deep beneath the Earth's crust, mantle, and outer core lies a solid inner core, a sphere of mostly iron, almost as hot as the surface of the sun. This inner core is crucial, as it plays a significant role in the dynamics of our planet. Surrounding this solid inner core is the outer core, a layer of molten iron and nickel. This outer core is in constant motion, driven by the heat emanating from the inner core and the rotation of the Earth. The extreme temperatures and pressures in the outer core create conditions unlike anything we experience on the surface. These conditions are so intense that they cause the iron and nickel to remain in a molten state, despite the immense pressure. It's here, in this churning cauldron of liquid metal, that Earth's magnetic field is born. The movement of the molten iron generates powerful electric currents. The molten iron, driven by the Earth's rotation and internal heat, flows in complex patterns, generating electric currents. These currents are not random, they follow intricate paths influenced by the Earth's rotation and the heat from the inner core. These electric currents, in turn, create a magnetic field that extends far out into space, forming what we call the magnetosphere. This magnetic field is essential for life on Earth. This magnetosphere acts as a protective shield, deflecting harmful solar wind and radiation from the sun. Without it, life as we know it would be impossible, as the solar radiation would strip away our atmosphere and expose us to deadly cosmic rays. Imagine trying to navigate a vast ocean without a map. That's the challenge we face when dealing with Earth's ever-changing magnetic field. To keep track of the magnetic North Pole's movements and understand the field's complexities, scientists created the World Magnetic Model, WMM. The WMM is a mathematical representation of Earth's magnetic field, updated every 5 years to account for the latest changes. Think of it as a constantly evolving map of an invisible force. The latest version, WMM 2025, incorporates more data and sophisticated algorithms than ever before, providing the most accurate picture yet of our planet's magnetic landscape. The WMM is much more than just a scientific curiosity. It's an essential tool for a wide range of applications, from navigation and surveying to resource exploration and military operations. Section 5. Navigating the Future Impacts on Technology. In this section, we delve into how the shifting magnetic North Pole affects various technological systems that we rely on daily. The magnetic North Pole's movements have real-world consequences, particularly for technologies that rely on accurate compass readings. This includes everything from traditional compasses used by pilots to modern smartphone apps that help us find our way. Navigation systems, from the ones in our smartphones to those guiding ships and aircraft, depend on knowing the difference between magnetic north, where the compass points, and true north, Earth's rotational axis. This distinction is crucial for accurate navigation. As the magnetic North Pole shifts, so too does this difference, known as magnetic declination. This shift can be subtle, but has significant implications for navigation accuracy over time. This means that navigation systems need to be constantly updated to account for the changing magnetic landscape. Engineers and technicians work tirelessly to ensure that these updates are implemented seamlessly. Failure to do so can lead to significant navigational errors, especially in regions closer to the poles. These errors can be particularly dangerous in the Arctic and Antarctic regions, where precise navigation is critical for safety. The rise of autonomous vehicles adds another layer of complexity. Self-driving cars and drones rely on a combination of GPS data and magnetic heading to navigate accurately. These vehicles rely heavily on precise location data, and even small errors in magnetic heading can have significant consequences. For instance, a slight miscalculation can lead to a drone veering off course, or a self-driving car making an incorrect turn. As we move towards a future of self-driving cars and drones, understanding and accounting for the magnetic North Pole's movements will become even more critical. The future of transportation and delivery systems depends on our ability to adapt to these changes. Section 6. Swarm of Knowledge, Unveiling the Secrets of the Core. To better understand the complexities of Earth's magnetic field and predict its future behavior, scientists are constantly monitoring its every move. One of the most valuable tools in this endeavor is the European Space Agency's SWARM mission. Launched in 2013, SWARM consists of 3 identical satellites orbiting Earth in a carefully choreographed dance. These satellites act as space-based observatories, measuring the strength, direction, and variations of Earth's magnetic field with unprecedented precision. Data from SWARM has already provided valuable insights into the workings of Earth's magnetic field. By analyzing the subtle changes in the field's strength and direction, scientists can infer the movement of molten iron in the outer core, the source of the magnetic field itself. Section 7. The Future of the Field, Predictions and Possibilities. While we've made significant strides in understanding Earth's magnetic field, many questions remain unanswered. Will the magnetic North Pole continue to slow down, or will it speed up again? Could we experience a geomagnetic reversal, where the magnetic North and South poles flip? Predicting the future of Earth's magnetic field is a complex task. However, by combining data from missions like SWARM with sophisticated computer models, scientists are getting closer to unraveling the mysteries of our planet's invisible shield. Understanding the magnetic field's behavior is not just about satisfying our scientific curiosity, it's about safeguarding our technological infrastructure, predicting potential hazards from space weather, and ensuring the continued habitability of our planet. Section 8. Beyond navigation, the magnetic field's protective embrace. The magnetic North Pole's wanderings might seem like a distant concern, something for scientists and navigators to worry about, but the truth is, Earth's magnetic field plays a vital role in our everyday lives, even if we don't always realize it. Think of the magnetosphere as our planet's invisible force field. shielding us from the constant bombardment of charged particles streaming from the sun, known as the solar wind. Without this protective shield, life as we know it would be impossible. The magnetic field also plays a crucial role in protecting our atmosphere. The solar wind can strip away a planet's atmosphere over time, as we've observed on Mars. Earth's robust magnetic field deflects the brunt of the solar wind, helping to preserve our life-sustaining atmosphere. Section 9. Our Magnetic Legacy, a Dance of Poles and Progress. The magnetic North Pole's journey is a reminder that our planet is a dynamic and ever-changing system. It's a reminder that what we perceive as constant and unchanging can be subject to forces beyond our immediate comprehension. As we continue to explore the frontiers of space and rely more heavily on technology, understanding Earth's magnetic field will become even more crucial. From protecting our satellites and power grids from space weather to ensuring the accuracy of our navigation systems, our magnetic legacy is intertwined with our technological future. The dance of the magnetic poles is a dance that has played out for millennia, shaping the course of life on our planet. As we continue to unravel its mysteries, we gain a deeper appreciation for the delicate balance of forces that make Earth such a unique and precious home.